Hi everybody, my name is Emmanuel and today we'll be presenting TGN, Temporal Graph Networks for Dynamic Graphs. This work was done in collaboration with my colleagues at Twitter. So graph neural networks are certainly becoming very hot in the ML community. We can see here some stats. Basically the increase between 2019 and 2020 of keywords in iClear 2020 submissions, and graph neural networks was the most increasing keyword, so certainly is gaining traction. And the reason is very simple, is that graphs are everywhere. So here we have a few examples. We can have social networks, we can have molecules, we can have functional networks of the brain, and we can have interaction networks of protein-to-protein interactions. However, processing graphs is not straightforward. So one of the big success story in machine learning is computer vision. And computer vision, we have images, we want to process them, and we can kind of think of graphs as generic version of images. So it will be the first thing one may think is, can we take what we have for images, so convolutional neural networks, and use it for graphs? However, images have specific properties which are particularly nice and they don't really apply to graphs, such as a constant number of neighbors, and also you can have a fixed ordering of neighbors. So you always have a neighbor on the top left, on the top, on top right, and so on. Whereas in graphs, you don't really have these properties. So nodes can have different number of neighbors, so they have different, what we call degree. And also there is no order of neighbors, so there is no way you can assign usually that a neighbor is the first or a neighbor is the second neighbor. So we need to kind of take into account these differences to build models which are inspired from convolutional neural networks but work for graphs. And so in the last 4 or 5 years there's been a lot of research in this field, and basically most of the models that were proposed can be framed in a message passing scenario. And basically the idea is that at each layer, basically similarly to how the representation for a pixel is updated by using a filter on its neighboring pixels, here we want to update the representation of a node by aggregating information from the neighboring nodes. And so here we can see that we want to compute a message between node I and j, which depends on the features both of I and of j, and possibly the features on the edge, if there are any. And here we see what's happening. So we want to, for node I, we're gonna have messages from all neighbors. So here we just have one neighbor highlighted, but actually we're getting messages from all neighbors, and then we're gonna aggregate them using some aggregation functions, such as mean, sum, or even attention. So this has been, there's been a lot of work like this for the last few years. However, one issue with these kind of models is that they're built for static graphs. So static graphs are graphs that are, don't change over time. Whereas it turns out that many, many interesting graphs are dynamic and they evolve over time. And also, most of the work that's been done for dynamic graphs is actually been focusing on a very specific case, which is called discrete time dynamic graphs, which are basically dynamic graphs that are represented as sequences of snapshot of graphs. So you have, let's say, one graph for January, one graph for February, one graph for March, and so on. Whereas usually in real life, many applications have what we call continuous time dynamic graphs. So which are graphs where an edge can appear anytime. We don't just have different snapshots, but each time has a timestamp. Nodes can come and go, edges can come and go, and we want to be able to have models that adapt to this very general framework. And Twitter, for instance, is a great example of a dynamic graph. And here we have a little drawing, so you can have users which, they have follow relationship between each other, and they have a specific timestamp. They also can tweet. They can post tweets at a specific timestamp. They can like tweets, and so on. And the timing information here is fundamental. So basically, knowing the timestamp of when an action happened can make you is a great predictive value on knowing what's going to happen next. So to basically model these continuous time dynamic graphs, we propose this new generic theoretical framework, TGN, Temporal Graph Networks, which is basically an encoder model which is able to generate a temporal node embeddings for node I at any time t, for any node I at any time t. And basically does so by processing the edges order in time. And the nice thing is that is a generalization of existing models for continuous time dynamic graphs. And the key insights of TGN are really two. So we won't have time to go into all the details, but the main insights are two. And these are two models that we find in TGN. And one is the memory. So what is the memory? The memory is basically a vector that we have for each node, which evolves in time based on the interactions that node is involved with. So basically, it's the dynamic state of each node, which represents, what we have seen for node I up to this point in time, and is updated each time we have a new interaction for I. And the second key point for TGN is the graph embedding module. So when we want to compute an embedding for node I at some time t, it turns out that is just using the memory that we have for I, the most recent memory that we have for I is not enough, but it actually works much better if we have an aggregation over the temporal graph, so we can aggregate information also from the memories of neighboring nodes in the temporal graph. So here we have a nice diagram showing the training and the modules of our models. So quite quickly we can go over it. So here we have the batch, and the batch in this case is a sequence of edges. So we have an edge between 1 and 2, which happens at time 1. So we have two flows of operations here. So one flow is we use the graph embedding module, which we were talking about, to generate embeddings for all these nodes at the time of the given interaction. So we have an embedding for node 1, for node 2, for the first interaction, and so on. And then we can use the decoder to compute the probability of having an edge between these two nodes, and this is going to generate our loss, since we actually want our model to be able to predict this edge. On the other side, we also want to use these interactions to update our memory, the state of our nodes. So to do so, each interaction generates two messages, one for the source of the interaction and one for the destination. So here these two messages are from the first interaction, these two messages are from the second interaction. Since a node can appear multiple times in a batch, we can have multiple messages for the node, and so we have an aggregator module which actually aggregates multiple messages from the same node. So then we get with one single aggregated message for each node, and then we use another we call memory updater module, which takes the previous memory and updates it using the new aggregated messages. So this basically is able to bring the memory up to date using the latest information. So some experiments here. So basically on this future edge prediction, here we want to predict future edges, and we see that our model obtains state-of-the-art results on 3 different data sets, and obtaining a large margin compared to other methods. And also here we have an ablation study, which I won't go into too much detail, but basically the idea is that all these blue ones are our different variants of our model, different implementation of the modules. And here, instead, Jody and TGAT are 2 different models. And in general, what we see here is that our model is able to obtain a much higher performance while also being faster. And different variants are faster or more accurate, and we have a trade-off. So in conclusion, dynamic graphs are very common, but so far have received very little attention, specifically continuous, in particular continuous time dynamic graphs. Here we propose TGN, which is a generalization of existing methods, and is able to achieve state-of-the-art results in a variety of benchmarks. And we also have a detailed ablation study which really shows the importance of different modules. Thank you very much, and see you at the poster session.